Hi, welcome back to another explained video. We're going to go through the 2005 HSC past paper question 21. This is going to be part of Module 6, Inquiry Question 2. And the major investigation we're looking at is two charged conductive wires. Okay, so two thin metal tubes, 1 meter long, were supported in a vertical wooden rack as shown in our diagram. The two ends were connected together, then the other two ends were connected briefly to a car battery. It was observed that one of the tubes jumped upwards as the connection was made. So it doesn't really matter which one we have, but let's say one jumped upwards. Okay? So the question is probably going to look at whether or not you know it's an attraction or a repulsion. So explain why only one tube jumped upwards. Okay, so what we could probably tell here is there is either a attraction or a repulsion force. But let's just have a look at the setup here. So we start off at the positive terminal and it goes into the tube. It connects down in this direction here and then it goes along this tube here. So this is a series circuit. Okay, if I want to use my right hand grip rule, so current is going in this direction here, okay, and we have magnetic field lines kind of circling back up this way. Okay, might just do it in a different color. And then along this side, my current is going in that particular direction, and if you use your right hand grip rule, your fingers are pointing down this way. Okay, so if I drew out my magnetic field in the top section here, if I look at this particular point here, I'll see that at the very top, we have the current coming towards you and the magnetic field going in this kind of loopy-loop direction. At the bottom one here, it's going into the page, okay, and it's looping around this way. So what you can see is the magnetic fields aren't joining up together. If they're not joining up together, that should tell us we are seeing a repulsion. Okay, so that's what we have. So how do we explain this? Let's firstly identify, what type of circuit it is. So this is a series circuit. Where the current is moving in opposite direction to each other. Okay. So what this does is it causes a difference in the polarity of the two conductors, causing a repulsion force, pushing one rod upwards. So that explains what happened in that one there. If we go down to the next question, it says each tube has a mass of 1 times 10 to the minus 2, and the tubes lie on the rack at 10 centimeters apart. What is the minimum current flowing between when that tube jumps? If I look at my formula sheet, the formula I'm going to use is FL over L equals 2. We can use mu naught over 2 pi current 1 over current 2, or current 1 times current 2 over a radius. I'll change color again. Okay, so in this case, we need to work out what I is. What we do know from the question, or at least from our diagram, is the wires are connected to each other. So if the wires are connected to each other, it has the same current. So I1 will equal to I2. Okay, so I'm going to rewrite this formula to make it into I squared later on. I know what this value is. This is just the constant on your data sheet. So if I just rewrite all that, and we're going to also move the length along. So let's just rearrange our formula first. So we have the length times, or force divided by length, times by the radius of separation. So times by the radius of separation. Okay. And we have mu naught 2 pi I squared times that. Okay. If you want, you can also move the other part across, so you can move the pi over. So we can get something along the lines of times 2 pi, because 2 pi times up here, mu naught is divided down here. That equals I squared. Okay? And so if I want to find my final answer, I root the final answer. But let's just do our substitutions. So what is the force? We know that in our situation here, at the very top, we don't actually know the force. It's not given to us in the question, but we do know that this rack is hanging on a shelf. Now, the thing that's pulling it down is the force due to gravity. Okay? Now, force due to gravity is equal to mass times acceleration. We're actually given the mass here, and we actually already know what the acceleration due to gravity is. So we can substitute that in as our force value. Okay? So it is 1 times 10 to minus 3. Just make sure it is. Or minus 2 times 9.8 over the length of the wire, which was 1 meter. Okay. Times by the separation, which is 10 centimeters. Okay. And then times 2 pi over mu naught, which is 4 pi times 10 to minus 7. So that's what we have here. Might just quickly rewrite it out to make it a bit clearer. So just get rid of this bit here. So we have F L times R times 2 pi over mu naught. That will equal to I squared. It's not very keen for me to write here. Well, we'll just write it here, I squared. Doesn't look like it's working today. Oh, we'll just write over here. So that equals to 1 times 10 minus 2 times 9.8 force over 1 times that, and then also times 2 pi over 4 pi that. Okay, so what is the answer of this question? Let's do a quick calculation. So my current squared is 4,000 or 49,000. If I square root that and take it to the nearest 3 significant figures, my current is 221 amps. All right, so it's quite a large current going through there, but that's how you do the answer there. The last question, it says, what is the implication of this result for power distribution networks? So what does a high current potentially do? So what are the implications? Well, what we do know is a lot of the power transmission lines that we have in the world, they are all connected to the same grid. So they're all in series to each other. So what that tells us is we need to actually keep a very low current. So to have a low current, to avoid the wires interacting with each other, or we can call them current carrying conductors. And so that's why we need to do that. Okay. If you want to have a look at other, playlist of Module 6 Inquiry 2 questions, there will be a little playlist along the side here. But anyhow, that is how you do the question. So a little bit of work there. That's how you do it.